And okay, so we're going.
I will go to the share screen mode. How's that?
Okay, great, great. That's great. We see that, and just had.
Paper ready to go here.
So I think we're. Yeah, I think we're ready to go. You can even put that little share screen down even more into the corner if you want to get it out of the way. But
Okay.
I want you to see us, but you know. What's that? Okay, so we got a couple students on their way. There was a overlap with another class period, but we're good to go, Steve. So take it away.
Okay. As mentioned, we're going to be talking about the vapor.
That's right.
Okay, this is energy rate density as a complexity metric and evolutionary driver. How's that? By DJ, and we have no idea how this is named, but I'm going to go with Chase on today.
Okay.
He is at Tufts University. They also listed at the Harvard University Observatory, Harvard College Observatory. So, but I think he's mainly at Tufts. And he is, I gather, by training a cosmologist. Okay, a cosmologist is different from an astronomer in the sense that astronomer studies, measures particular things, looks up into the sky, looks at planets and galaxies and things like that. A cosmologist is one who considers how the universe as a whole works. So he studies the physical system is the universe as a whole on the large scale. Technically, they also do cosmogony. Okay, they don't typically have cosmologists and cosmogonists. Okay, cosmogony is how the universe evolved from how it came about in the first place, which the current accepted theory is the inflationary version of the Big Bang theory. So anyway, let's forge ahead. Let's see, slideshow, thank you, from the current slide. Okay, so there it is. Now, I'm going to talk about one more thing here, free energy. We've been talking a lot about thermodynamics in terms of entropy. Okay, that any system to proceed spontaneously, or any process to proceed spontaneously, has to generate a certain amount of disorder in the universe. Another way of viewing this is the free energy approach. The free energy approach refers to the amount of energy transferred that can be used to do work. So in other words, rather than think about how much disorder we have to make, or a better way to think about it, how much energy we have to degrade and release to the environment, let's say in the form of heat, we emphasize the other side, which is what's the maximum amount of energy that I could use to do work. Okay, so think of it this way. It's like thermodynamics says when you transfer energy to a system, a certain amount is available to do work and a certain amount must be sacrificed to the gods of entropy. So the free energy approach, free energy, literally means free as in available, not free as in of no cost. Okay, it literally means this is the available energy to do work. So this is the energy that we have to create and run our civilization, create and run our own bodies, so on and so forth. And again, when we think about physical processes, most of the entropy is lost, most of the energy is lost to the environment, it's heat. So let's think about your car. Okay, your car generates a certain amount begins with a certain amount of energy that comes from burning gasoline, exploding a certain amount of gasoline in the center of your engine. A certain amount of that energy can be used to drive the pistons to make the car move forward. A certain amount of that energy is lost. And you have to really think about this, okay? So much energy is lost to the environment in the form of heat that your car has to have a liquid cooling system. In other words, if you think about like an old motorcycle, like a Harley, okay, where you have an engine that has no liquid cooling system, that's called an air-cooled engine. In other words, the engine can be cooled, the waste heat can be taken away simply by the motion of the vehicle through the air. For a car, okay, we've long since passed that point where air cooling is effective. We now have to wrap the engine with liquid so it can carry the energy away faster than that. And the alternative is, if you don't do that, of course, the engine melts, seizes eventually. That's what they mean. The piston gets sufficiently hot to stick to the cylinders. So,
can I ask a quick question, just because
Sure.
you're here and it may be not germane, but I can't resist. Is liquid a better coolant than gas, i.e. air?
absolutely.
Because why is...
Heat transfers to energy heat transfers through a liquid faster than it does through air.
What about a solid?
Solid would be great, but it's really, really hard to circulate a solid.
Okay.
You know? So for example, when you're cooling, Americans use water to cool nuclear reactors. The Soviets use liquid sodium. Okay, liquid sodium will transfer that heat a lot faster than water will. But the problem with it is it's nasty material to work with. So it's a question of speed of transferring the heat away. Your energy generates heat, your engine generates heat sufficiently quickly that if we just relied on it trying to cool by passing heat to the air, the engine would eventually effectively melt before it could move on. Is that good?
Mm-hmm. Yep.
Now, again, you can restate the second law of thermodynamics in terms of energy, entropy, or free energy. The entropy version emphasizes the energy loss to create disorder. So in other words, the entropy must increase. Free energy approach can also be there, and it talks about how much energy is available for work. Okay, so let's actually look at that approach. Okay, a lot of math here, don't freak out, you don't have to know any of it. This is the first law of thermodynamics in the physics approach. Now notice I've written this before with a plus sign. The difference here is now W is the work done by the system. So if as the system, the engine is doing work, energy is leaving the engine. Okay, that's the appropriate sign we want for this approach. Okay, so here I have it. The second law of thermodynamics is based, this is the first law. The second law is based on entropy. This is the Clausius definition of entropy, remember. It is the change in entropy of a process, which is equal to the heat you emit divided by the temperature at which you transfer that heat. Now notice I can rearrange this so it has the form Q is equal to T times delta F. So I just multiply by T, and I can now substitute into that equation right there to get this. The change in energy is equal to T delta S minus W, or, rearranging that slightly, negative W is equal to E minus T delta S. In the best case scenario, we have the maximum amount of work. Don't forget, this can always, we all have cars, okay? As we drive our car over time, it gets less efficient, okay? So we're only concerned about what the maximum amount of energy we can get from burning that fuel in a heat engine. That maximum amount, okay, that combination which maximizes it is called delta F, the free energy, okay? That is the most work you get out of the system. Having said that, this is what the second law becomes. It says for a spontaneous process, the change in free energy must decrease. Okay, the change in free energy must be negative. In other words, free energy must decrease as the process goes in the same way that entropy must increase. Now, why is that? It's easy to think of, really. F is just thermodynamic fuel in its most fundamental sense. If you're driving your car, it does not surprise you that the gas gauge goes down. Okay? It would probably surprise you a lot as you're cheerfully driving your way to New Orleans for a big night, and the gas gauge kept going up, okay, as you were driving. So that's what we think of this is. This is literally the ultimate thermodynamic fuel. This is the energy available for you to run this process. As you run that process, the free energy, available free energy drops. Okay, everybody good with that?
Yep.
Okay. Now, here are, we're going to look at some Kazon's results, and I assume you've seen the paper, so I didn't put a lot of words around this because you got a whole paper in front of you. Now, Kazon's concept was this. He says that a way to measure the complexity of a system, okay, is to think of this as, and especially on page 28, right at the top on the right-hand side, he said, this then has been, continues to be my working hypothesis. Energy rate density, a mass normalized in parentheses energy flow, denoted by capital Phi sub m, is perhaps the most common currency available to work thermodynamically to build structures, evolve systems, and create complexity. Now notice the free energy is important. When he looks, for example, this graph right here, okay, right, delta, this is the amount of energy you need to create and continue human society. This is not telling you anything about the waste energy you have to dump into the environment. This tells you literally the amount of energy we need to do things, okay? So this is the thermodynamic best case scenario. We need, and the unit he gives, and I'll talk in a second about that, is 500,000 ergs per second per gram to keep human society going on planet Earth. Now, how efficiently we do that can minimize the amount we have to dump in the environment, but nonetheless, this is what we need. So let's talk about these units here. It's kind of a funny unit. He uses ergs. Okay, an erg is the CGS unit of energy. It's a really, really tiny unit. So he uses ergs per gram. The metric unit would be joules per kilogram. And there's about 10 million ergs in a joule. So this is a weird sort of thing. So this would go up by, so I would replace this with 10 to the negative 7th joules. I'd have to replace that with 10 to the negative 3rd kilograms. So I could divide this by 10,000.
Do you think he's doing that, Steve? He's using such a tiny metric because of sort of his cosmological background, where apparently there's so little energy?
I'm surprised. No. Cosmology uses enormous amounts of energy. So I'm kind of surprised at this, although I do suspect one of the reasons is this right here. And that's what you're saying, effectively. The sun and the Milky Way would be as 2 or 0.5 ergs. If you convert this to joules per kilogram, you go down by a factor of 10,000.
Yeah. So
this would be 50 joules per kilogram. Okay, but the sun would be 0.0002. So that's probably why he's using this unit, just because it keeps things as whole numbers, especially if you're going to work with the sun. So I'm not surprised that a cosmologist would use this. A biologist would probably use the kilogram, the joules per kilogram. So it's not really that critical that you understand this, but all you have to realize is the sun output 2 ergs per second per gram. That's how fast the sun is burning through free energy. The Milky Way burns through it even more slowly. The point is, the sun and the Milky Way are effectively pretty simple systems. Okay, the sun is basically a big ball of hydrogen that's only burning its way through the liquid helium a big ball full of gaseous hydrogen, cheerfully burning its way through to primarily, at this stage, helium. Okay, the Earth geosphere, the planet as a whole, okay, so this is the planet and the atmosphere, goes through about that much energy per gram. Now notice, remember this, the gram part is critical. The sun is much larger than the Earth. So if you multiply by the mass of the sun, you multiply by the mass of the Earth, the sun's putting out a ton of energy, far more than the Earth. But per gram, okay, that's the point, the Earth is going through more energy than the sun is. You get that distinction?
Mm-hmm. I mean, you guys got that? Everybody good?
So here's a way of thinking about it too. A hummingbird goes through straight out energy faster than we per gram because it lives so quickly. Okay, it moves so quickly. But this is human society we're talking about now. So to maintain the human civilization, this is the amount of energy it takes. To maintain the animals in general, this is the amount of energy it takes per gram. So this is human society. Now what does that mean? That consists of all the people,
Okay,
all the houses, all the planet, all the roads, all the planets, all the buildings, all the roads, everything we have.
All right, hold on, Steve. Maddie, you got a question?
I think he was starting to answer it. I was wondering how the energy for human society was like what goes into that to determine like what makes up our energy.
How does he calculate it? How does Chaisan get that 500,000?
If we go to the, you go to that last section where he talks about us. Oh, gosh.
It's one of the interesting things about this article. How does he get these things on the same scale?
Yeah.
You know? Yeah.
Oh, it's not that hard. What he figures out is what we go through. For example, we all know this trick. How many calories do you go through in a day? How much food do you have to eat?
Over
So
3,000.
A 2,000 calorie diet, right?
Okay.
So that's a measure of how much energy it needs to keep you alive. All right, that's a good indicator of that. Now the average American goes through something like 200,000 calories a day of energy to survive, counting in place the amount of energy you go through in terms of electricity and gas and the food you eat yourself. So this number has been stated in the following way, which is really interesting. Every American has effectively 100 energy slaves. Okay? In other words, the energy you go through in a day could support yourself and 100 other people. Okay, if it were just raw energy. So you basically are using the equivalent of 100 human beings worth of energy to do your stuff. To you know, from me to present this presentation to you folks down in Shreveport. That takes a bunch of energy. Drive home, watch TV, cool my house, heat my house, whatever. So we go through a lot more energy than it does to absolutely keep us alive. Now, one way you can figure this out is to literally sit down and add up the net amount of energy that people are going through on a daily basis on planet Earth. Does that help?
Yeah, well, say that last, I'm sorry, say that last thing again.
This is no, we have good estimates of this. We have good estimates of how much energy human beings are going through on a daily basis. The United Nations, U.S. government keeps track of these kind of things. But these are not hard numbers to come by. They're based on the amount of resources we're going through in terms of gas or electricity or food. And then you can figure this out for the planet. So there's good estimates of this. Notice, is it exactly 500,000? Of course not. Okay? It's, you know, it's probably, if you actually calculated it accurately, you know, it would be 498,243.7892. You know what I'm saying? That would be a well-defined number. But this is a good estimate of how that works. Again, it's based on the amount of money, the amount of electricity we're generating in the grid, the amount of gasoline we're going through, things like that.
What about the other end, Steve? I mean, I was, you know, sort of comfortable with that, but not being a, you know, a cosmologist or even an astronomer or even a student in those fields. I mean, the sun, I think of the sun as being a really hot furnace that's, you know, a lot of energy is being produced there.
The sun's easy though.
Okay.
The sun's a big ball. Literally, we can calculate the amount of energy radiating out of the sun per unit area. I mean, that's not hard at all.
But it's that per unit area, I guess, that is what brings it down to.
No, it's per gram, the gram part. The sun is an enormous ball of thing, but it weighs a lot more than the Earth.
Oh, I see. Okay.
That's the point. This is higher because if we took the amount of energy directly coming out of the sun, which I think he has it here, let's go to the sun part. Okay, physical evolution of the sun. The sun has a luminosity, okay, of 10 to the 33rd ergs per second. Okay, that's the actual energy coming out of the sun. Okay, now the mass of the sun is about, interestingly enough, 10 to the 33rd grams. If you do the division, the sun is doing 2 ergs per second per gram. Okay, and that's why you get that. Now the Earth, do they talk about the Earth here? Let's see, where's the Earth gone? Okay, no. It's later in the paper, let me look. Here we go. Living systems generally require larger values inside than inanimate objects to maintain tissue growth. Plants, in particular, on average, need 1.7 times 10 to the 11 ergs per gram photosynthesizing biomass. So the sun is easy. I suspect the Earth is harder to figure out. I can't find the actual point where he talks about that.
I mean, looking at his chart, where it's 2 ergs per second per gram for the sun, it's
Right.
75 ergs per second per gram for the Earth's geosphere, right?
Right, which is the Earth. Everything on here we have. And that could be measured literally by the following distinction. I know it's going to sound funny, but that's a measure of the energy coming in from the sun that hits the Earth minus the energy going out that's radiated back out by the Earth. We probably have good estimates of that from satellites, and that's a good estimate of the energy flow through the planet, because the only other energy source available to us on the planet would be nuclear fuel and fossil fuel. And by fossil fuel, I mean anything we burn, any like wood would be included in that as well. So that's not that hard to estimate in general. Now, the interesting question for me is how we get human society trickier, because what he would have to do is figure out the amount of energy directly associated with human society and then divide by the mass of our society. That's really going to be more of an estimate.
Yeah.
It's going to be the estimate divided by the mass of all the people on the planet. Actually, it's probably pretty easy. Divided by the mass of all our stuff.
Mm-hmm.
So this includes all of our iPhones, all of our buildings, all of our cars, all of our whatever we use to run our society, boats, planes, ice cream cones, whatever, lazy boys, okay, all that kind of stuff. And there's ways to I'm not surprised you can estimate these things.
But just before we leave this, sorry, Steve. So energy coming in subtracted by the energy going out, right?
Uh-huh.
And so the sun versus the Earth on that, I mean, the Earth is not luminescent, right? So we don't see it creating energy.
The Earth glows in the infrared.
And in heat, right?
Which is the infrared.
Okay.
Yeah, so in other words,
Okay.
if you can see the infrared, the Earth will be glowing like the sun.
Okay.
That's called black body radiation. That's a good way to track everything. So yes, you're going to laugh at this. Everything glows. It just the sun glows in a wavelength we can see. Human beings, you put on night vision goggles, that's because you can see infrared. That's what they do for you. And all of a sudden people are glowing because that's when you heat something up like a piece of metal, it glows red hot. Okay, we see it start to turn red.
Mm-hmm.
Human beings and everything at about room temperature are glowing infrared hot. If you could see the infrared, we'd be glowing. Is that good?
Yeah, that's good. And so the bigger difference between energy coming in and energy going out versus the sun and Earth, which is it?
I mean, say it again?
Which has the bigger difference between energy going in and energy going out?
The
It would be.
sun is putting out energy at a particular rate. You could figure out the amount of energy the sun has by, this is the amount of mass it has, this is the amount of hydrogen it has, this is the process by which hydrogen burns, it leaves the sun, okay? The Earth gets a certain amount of energy in from the sun, we burn a certain amount of energy in fossil fuel, et cetera, et cetera, et cetera, which is basically stored sunshine, and we kick out a certain amount that goes off into space. Ultimately, the energy leaves the planet in the form of infrared radiation.
Right, and what I'm getting at is in terms of which engine is more efficient as you go from sun to earth, to plants. It's getting more efficient, right? Or am I?
No.
No?
No, it's not getting more efficient. We're going through it faster to maintain the complexity. The Earth is a more
Okay.
complex place than the sun is.
Okay.
That's what this is indicating. It says, look, the Earth requires roughly 37 times more free energy per gram to maintain its structure than the sun does. The Milky Way only requires 0.5 ergs per second per gram to maintain its structure. Now, of course, this is in general because there's a lot of stuff in the Milky Way that's a lot simpler than us. And that's why this has less. The sun, for example, this basically, the Milky Way is averaging everything above it to some extent, and every other planet. But every other planet in human society weighs nothing compared to the Milky Way.
Mm-hmm.
Yes? Good?
Yeah, good.
Okay. Okay. Now, so here's a good way to picture this. This is how the Milky Way is burning the energy density as time goes on. Okay, so this is, back up to the present. This is going back 12 giga years. Okay, GYA, giga years ago. All right. So the universe started about 15 billion years ago. But this is 12, and then the universe starts to go through more and more rich free energy faster. Suddenly, it creates stars. Stars are better at going through free energy than the random gas. The Earth, condensed, is better at going through energy than the sun. Plants are better at going through energy than the Earth. Animals are better at going through energy than plants. Human beings suddenly build a society. Now, these animals include, not just their bodies, include animal societies, so the herds and the beehives and whatever, okay, that you have. The plants have a society of forests, for example. Human society goes through energy much faster. Okay, we're good with that?
Yeah.
Okay. Let's actually take a peek at this. This is how the plants do it. Okay, and I just included this because he talks about it so much in here, but to be honest with you, I'm not a botanist, so I'm not the best person to talk about how this evolves. What's really interesting, though, are these C4 plants. C4 plants literally mean the plants that we have bred, genetically engineered to feed ourselves with. So this is stuff like corn and sugar cane, stuff like that we have evolved. Okay, those plants they run through energy very quickly because they store a lot of energy. So the modern version of corn and wheat store more energy in the form of glucose and proteins than wild plants did, and human beings have evolved those because then we eat them. Or we not only do we eat them, the other thing that happens to a huge amount of these plants, the C4 crops, are we feed them to the animals. Okay, so we feed them to, this is, cow feed, cattle feed. Okay, the pigs and the cows eat these, and then we eat the pigs and the cows. Okay, because we like meat. If you will, a pig and a cow is a way of concentrating energy even more than a piece of corn. There was a famous saying, there's more energy in a rat than a root, which is why human beings, at least as far as we know, eventually, at one point we split into two groups. Okay, we would go Homo robustus and Homo erectus. And Homo robustus were the plant eaters. okay? They're not what we picture. They had big, thick, heavy jaws because they would chew roots. Okay, naturally occurring plants are not as, are not as available, it's not as high energy as the kind we have today. And the other kind, Homo erectus, were meat eaters. Okay, they ate other animals. They're the ones that we descended from, the Homo erectus. Okay, because the energy flow, in order to have a brain as complicated as we do, is much higher than it is to have for an animal that's not as smart. So that's one of the reasons human beings have to go through a lot of stuff, is because per gram, our brain is bigger.
And this is also why, isn't it, cats and dogs that are basically predators are napping all the time, whereas cows and horses and herbivores are walking around munching, right?
That's exactly right. That's also why there have to be fewer predators than prey.
You're right,
So
which
there's
we went
always-
over last time.
Yeah, there's a lot of energy stored in the plants, but it's lower quality. Then there's more energy stored in the food animals, the things the predators eat. The predators go through energy very quickly compared to the cows and the herbivores.
Is there a this is laden with meaning for me. I mean, is there a principle that this is sort of referring to?
This is Chaitan's point. He's saying that what we think of as complexity seems to correspond to the rate of free energy flow through that particular system or object or organism. So what we tend to think of as the more complicated energy-dense plants, okay, apparently correlate perfectly with this kind of a rate. If you plot, for example, let's go to the next one. This is humanity, okay? Humanity went from hunter-gatherers to agriculturalists, and it was a gradual rate. Okay, the agricultural societies went through energy at a higher rate than hunter-gatherers because they had more energy available to them. So they could create a civilization that went through more energy. The industrialists were a huge increase. When we started going from agriculturalists to being industrialists, okay, folks, now listen carefully to this, so this is the key distinction. The agriculturists were going through CO2 neutral energy sources, okay? Everything they used as an energy source had been recently alive. They burned trees. They ate food, okay? That was what they went through. The difference between the hunter-gatherers and the agriculturalists was the agriculturalists grew their own plants as opposed to went out and found it. They grew their plants and they either ate them or they fed their plants to animals and then ate the animals. So this is the age of agriculture and husbandry. Remember, husbandry means the creation of animals, or rather the maintaining of animals for ways to store energy. There's a great argument out there, is a cow a tool? You know, a cow is simply a way human beings use to store energy. Because a cow will store energy at a much better rate than corn will. Okay, meat has more energy than per gram than plant matter does. Unless, of course, you do what people do, which is we create things like sugar cane, which has high density, and then we distill out the energy to make, let's say, corn syrup, sugar or corn syrup out of corn, and that has even higher energy density. The industrialists, okay, see right there it is. Why does it suddenly go up? Because the industrialists start burning fossil fuel. Fossil fuel is plants that have been turned into concentrated energy sources for hundreds of millions of years. This is why the industrialists can go through a lot more energy.
You there, Steve? I think you've
What have I done?
You're okay. You've wandered off the screen a little bit. I'm going to close the door.
Okay, hold on, let me go back. I'll go look at that. Preview.
You're still a little bit off center there.
Okay, hold on.
You know, I
There I am. How's that, better?
Yeah, that's good. That's good. Kind of
That's better?
yeah, I mean, I got more of you. You're not, I got like two of you. You're sort of doubled up there.
I got rid of my pictures. I got rid of my slides. Now you see the slide again?
Yeah, you're not on slideshow mode, but we see them. You might want to go to slideshow mode.
Okay, well this is the picture, and you guys have the paper, so you can see what the idea is.
Yeah, and can I just, you know, there's an important question here, right, guys, in terms of the industrialists started burning plants that have, and you had some phrasing there about what the plants did and why suddenly, you know, why it's sort of more concentrated energy, plants that haven't been alive for, you know, 1,000 years versus those that have recently died.
Petroleum and coal and natural gas, which are the three primary forms of fossil fuels, are the remnant of 100 million years of plant life, which has been concentrated down by geophysical processes into a more concentrated energy source. Biofuels, for example, okay, we hear that phrase. Biofuel simply means a burnable fuel, a burnable hydrocarbon source that comes directly from things that were recently alive.
Yeah. So
a fossil fuel means it was alive a long time ago and it's been slowly being turned into natural gas, oil, and coal. Okay.
And that's very you know, interesting. I mean, so is there something about you know, energy or something that focuses it like that makes it into a more compressed, usable sort of form? It's like give energy time and it'll turn into free energy or something like that.
No. Well, it is, that's true, but what you want to think about is this. The hunter-gatherers and the agriculturalists were using plants to collect some of the energy hitting us from the sun. Plants are solar energy collectors. Not very efficient ones, but they are.
Right.
So we use them to collect the energy from the sun and turn it into a food we could eat or a fuel we could burn to keep ourselves warm. Once we became industrialists, okay, we needed things coming in at a faster source. I mean, you can do industrial work using wood as a fuel, okay? But wood, you rapidly run through it. You deforest this place very quickly. You need higher energy sources. So the most easiest ones we had were the solid version, which was coal. And the brick had coal at first. They used coal to run the trains and to run the engines. Okay, coal was the major source of energy for the primitive mills and the primitive agriculture, industrial methodologies we started using in the late 18th and early 19th centuries. So we were going through that pretty fast. The technologists, notice, are going through it slightly faster. Okay? And the reason is our society is far more information rich than it was 100 years ago. Think about it, guys. Once upon a time, you had maybe a personal library that consisted of a couple of hundred books. If you had to figure out something else, you had to go to the library downtown and look it up in a book. Now, a third of the planet can sit at a computer, type into Google, and have that information instantly.
And don't you think, Steve, that the one reason we're teaching this course right now, you and I, across these disciplines and stuff like that, is because of the density of information that's available now through the internet and stuff like that?
Absolutely.
Yeah.
Absolutely, there is no question, this is a huge advantage to us. I go home at night, and I have a vast selection of entertainment possibilities available to me. You know, I have all the cable channels, I have all the books on my Kindle, I have all the movies available to me on Amazon Prime and Netflix. That's a vast thing at my fingertips in terms of entertainment.
Let
200
alone
years ago,
the homemade stuff at the micro level, like what are where they do it's a website you go to for little skits on various stuff and they try different stuff, and you guys are on
YouTube.
Not YouTube. It's more cutting edge and sort of they've got studios, they make skits and stuff like that.
Yeah, but just, I mean, think of the information content of YouTube.
Yeah. No, right.
It's vast.
Yeah.
Okay, think of the information content of the internet. This is the recent thing we created. What are there, 2 trillion web pages at this point?
I know, so it's mounting up. Yeah. But Steve, let me go back to the fossil fuel, okay? I mean, it's as if anything that we take anything, I mean, you're the physical chemist here, right? We take anything and you let it sit for long enough. And you take that chair that's sitting ahead of me, you let it sit there for long enough, and it becomes something else. It becomes a more usable form of energy in terms of fossil fuels, right? I mean, why are dinosaurs more sort of burnable, you know, now than they were 1,000, million years ago?
They're not. They had more energy once upon a time. It's just now it's concentrated. In other words, the biosphere at the time of the dinosaurs had a certain amount of energy in it, okay? We've just been accumulating that energy. You don't think of it as concentrated, think of it as accumulated energy. This energy accumulated over 100 million years, more. Now, we're gonna burn it all in 5 centuries.
Yeah.
So is it like a wine, like it gains more and more energy?
Is it like a what, did you say?
A wine.
A wine. That it gains more and more energy.
Over time.
Leave it to the students to bring up alcohol. But yes.
No, but that's a good point. I mean, we're not saying that if you leave something sit, it increases in energy value. It doesn't. It degrades in energy value. But some of it stays usable, and if you let it accumulate over 100 million years, you get a whole bunch of it. And then you can start burning it. So suppose, here's the way to think about what we've done here. Students won't relate to this, but Lauren will, okay? Lauren, I assume you've got savings for retirement?
Yeah, a little bit.
Sure, okay. You've been saving your whole life, okay? The idea is, when you retire, you're gonna have a pot of money. You're no longer gonna have a job. You're no longer gonna have any money coming in. So you're trying to live off that pot of money, okay? Now, hopefully the idea is, when you retire, you want to live, ideally, you want to live off the drawdown, okay? So in other words, you want your basic nest egg of money to sit there and it generate enough income that you can live off generated income. Otherwise, you have to start spending the income itself. Now imagine, suppose, I'm not saying you, I assume you're a wealthy Southern professor, but let's suppose like many people in the United States, they're gonna retire with, middle class people, $1 million in the bank. If they just start spending that $1 million, okay, to live, not invest it, they take that $1 million out, they stick it under their mattress, and they start spending it. That's what we're doing with fossil fuels, okay? This is the money we accumulated over all our lives and spent through going through it. We put $1 million of it. How fast will we spend through that? Well, if you've been living your whole life, let's say on $70,000 a year, or let's say $50,000 a year, you'll go through it in 20 years.
And the reason that I can go through it so fast, right? The reason that, because Maddie asked that question about, is it like wine? And she heard your answer and she mumbled, oh, so it's not like wine.
No, it's not.
It's not, but in another sense, what we're saying is we've we develop a system of complexity that allows us to burn through something, a single bottle, right? I mean, I don't know how many, grapes goes into, how much grape juice goes into that or something like that, but I evolve a lifestyle, for example, that allows me to burn through my retirement savings very quickly. And
right. But that's probably the same lifestyle you've had all along. If you actually, let's say, make enough money, so your whole life you've been spending about $50,000 a year, but you have also made enough extra to invest, so that by the time you were done, you had saved $1 million.
Mm-hmm.
Okay? Well, that means, let's say you retire at 70, that means it took you 70 years to put aside $1 million, and now you're going to go through it in 20.
Mm-hmm.
But that's okay, because we assume you're going to die.
Yeah,
at night.
hopefully, right.
Okay? So that's the way that works, not hopefully,
Yes.
So this has been the idea. The Earth has been storing energy because it's been accumulating energy from the sun. This is sunshine. Sunshine was converted by the plants into hydrocarbons, carbohydrates, some of which sunk into the ground and simply didn't degrade very quickly. So what we ended up with was the accumulated sunshine energy of 100 million years.
Mm-hmm. Mm-hmm.
Okay? And now we're going to burn through it. Let's be generous. We're going to burn through it in a millennium.
Oh yeah, that's generous.
But are we not still accumulating?
She said, are we not still accumulating? Are we not still accumulating that sunshine energy?
We are, but if we okay, imagine if all the oil and all the fossil fuels on the planet have accumulated over 100 million years, and it's probably more like 4 billion years, okay? Then how much more can we accumulate in the next 1,000? Nothing. Small potatoes, okay? We'll be going, the agriculturalists didn't worry about this at all because they only burned through what they could grow. So what you're saying is, and this is perfectly sensible, it would be really nice if the human race would convert purely to biofuels. Biofuels are the stuff we produce on the fly.
Yeah.
So that's renewable. That's a renewable resource. Okay? If we tried to support our current society by just cutting down trees and burning them, we wouldn't have any forests left very shortly. Imagine if the cars ran on trees. Imagine if we generated our electrical power by burning trees, by burning wood. There wouldn't be much left. We're generating our power by burning coal, largely. Okay? If you see these trains full of coal go by, they go by every day. Okay, there's billions, there's tons and tons and tons of coal being dug out of the ground. That's where our power comes from. Okay?
Mm-hmm.
We're gonna, so if we said, okay, no more oil, no more natural gas, no more coal, no more nuclear reactors, okay? All of a sudden, we have to power our society purely by what we grow. So trees and the crops, okay? Trees and the crops. Our civilization would not be as complicated, and we certainly wouldn't be supporting 7 billion human beings. One good way to think about this is pre-industrial, the planet had maybe 500 million people. Post-industrial, we have 7 billion, because we can support that much more people. If we go back to just living off the plants that we have, the population of the planet will go back down to under 1 billion people.
Okay.
Because we just won't have enough energy to support this many people.
So Steve and I were talking the other day about this, and don't stray from your face shot there.
Yeah, I'm not. What I am going to do though is switch the. You seeing the slide at all?
Yep.
Okay. So this is exactly the point here. For example, we can only become so efficient. The second law of thermodynamics says efficiency maximizes at a certain point. So our only real alternative to continue is to come up with an alternative to fossil fuels, if we run out of those. Fusion, which is nuclear power by fusing hydrogen, is a great energy source. We have millennia worth of fusion energy just in the oceans. 1 out of every 6,000 water molecules has a deuterium at one of the hydrogens occurs with deuterium. Deuterium can be used to burn in fusion reactors. So 1/6000th of the Earth's oceans is a fabulous amount of energy.
Yeah.
The problem is we haven't been able to make fusion reactors work yet.
But when we do, it'll be much more efficient.
It's not efficient, it's just more energy. There's a ton of energy locked up in the ocean.
Okay,
We're going
okay,
to start
okay,
burning
okay.
that.
I see. You're still, yeah, you're worried about the universe. I know.
No. But you keep thinking efficiency. It's not efficient.
It's not efficiency, because you're going to be giving off heat, and
Right. We've
yeah.
always found a bigger pile of coal to burn.
Right.
Okay, we're burning, the fossil fuels are great. We found much better, a big pile of concentrated fuel. That were the fossil fuels, okay, as opposed to the burning of wood. Then, if we manage, we also do this, we have uranium, okay? If we said, oh, screw the radiation, and just build as many nuclear power plants as possible, we have a lot of energy, okay? Uranium and plutonium are really concentrated energy, and that's not from the sunshine. Okay, that's a totally different source of energy. And that would keep it going for a couple of centuries. Fusion would keep it going for probably a couple of millennia. And by that point, hopefully, we will have gone to another planet and exploited its resources.
Okay, now I just want everybody to hear that, okay? So, pessimistic Desjardins did give us an out there that we can go into space. I mean, a few millennia, right? That would give us a chance to develop a chance to colonize the solar system, right? I mean, do you believe that, Steve? You think that could, you know?
Absolutely. Oh, well, we do that or we go extinct eventually. I mean, it's that simple. I mean, this is not pessimism. This is the way things work.
Right.
And I mean, people love to go into denial about this, but that's not the way the world works. We're never going to get to a point on this planet where we're energy neutral. We're going to continue chewing stuff up. All we can do, I mean, the big thing is the sun's going to burn for another 5 billion years, but eventually that burns out too. So in 5 billion years, the sun goes gas giant on us and destroys our planet. So we got 5 billion years anyway. That's about it. Okay, before that happens. But of course, 5 billion years is not exactly going to affect real estate values. It's like,
right.
Ooh, we're going to go in 5 billion years. Kind of thing. That's a huge amount of time. So we have other things. So, there's no question. Most people realize. I mean, Stephen Hawking talks about, of course, we have to go to other planets. We have to go to Mars so we can use its resources. We have to, Jupiter is a big ball of hydrogen. If we can get to Jupiter and can make use of it, that can burn that hydrogen forever. There's energy sources out there. We have to get to them and exploit them, though. Because we can't, efficiency is only going to buy us so much time. We just need more energy.
And Chaison's point, sort of, is that it'll be found, isn't it? Partly. Okay, so we go extinct, and you guys can jump in here at any time you want, but we've got 15 more minutes with Desjardins, and we're not going to release him before that point.
Think of this. The energy, there's no question. We can maintain ourselves. We know there's other energy sources out there. We have to go get them. As long as we have energy sources, we can cheerfully move forward. This is what I call the myth of efficiency, however. Okay? We can't simply become so efficient that we're good.
Right.
We have to, if we want to use less energy, we have to simplify things. We have to, Jimmy Carter once made the comment, wear a sweater. Wear a sweater is basically simplifying, you wear clothing to compensate for temperature differences rather than adjust the temperature of your house. Or, you actually burn through more calories if you're colder in the winter and warmer in the summer. Your body personally has to burn through more calories to keep you alive in the heat and in the cold. than what we do, which is we heat our houses in the winter, we cool our houses in the summer. So that's not a problem. We just have to be willing to burn energy. I mean, it's a question of which gets us first. We have to be careful. So, for example, we are currently making a decision that it's safer for us to burn fossil fuel and take the risk of climate change and its effect on us than it is to use plutonium to generate electricity and have the danger of a radiation problem or meltdown.
Yeah.
I mean, burning fossil fuels has drawbacks. Okay, the drawback is climate change. Now the question is, if you don't believe climate change is happening, then that's fine, but that doesn't mean it's not happening. And that's the problem we have. As we put carbon dioxide into the atmosphere, and that's a direct result of burning carbon-based fuels, the atmosphere is changing. There's no way around that. We're burning fuel faster, of course there's more carbon dioxide. The question is that what's causing, this is the whole difference of, is there, the Earth is retaining more energy, and is that anthropomorphic or anthropogenic? In other words, are we the cause of that? Notice the interesting problem. If we're not the cause of it, then we're just screwed. And climate change will happen, we won't be able to stop it. Because we are seeing changes. We are seeing the ice sheet start to melt. I mean, we don't have to believe it, and it really doesn't matter, because quite frankly, Lauren and I will be dead. You guys are going to be the ones to find out this empirically. Because, we'll be gone by 2050 easily. You guys will still be around, so you'll get to tell us how that all went.
Yeah, well, thanks, sunshine.
Yeah, I mean,
You're leaning to your right there, Steve, but we're only seeing your shoulder. There you go.
See?
Yeah,
it's
so
funny too, because I suspect from what I'm saying, you probably think I lean to the left. But
yeah. Well, so
I mean, people realize this. I mean, this is like rebuilding a pipeline to Alaska. That's an energy source. I mean, that's why we do things like that. Fracking.
Yeah.
Fracking has been a great discovery. The United States and Canada have a bunch of fossil fuel energy in the ground. We just got to get it out. The Canadian tar sands up in British Columbia contain more hydrocarbon energy than everything in Saudi Arabia.
Wow, really?
It just doesn't contain it in a form we can just pump out of the ground. We have to separate it from the dirt. But, we're doing pretty well. I mean, there's a bunch of energy buried under South Dakota, if we just keep fracking. Yeah.
Well, and you're talking to, Shreveport, Louisiana, which is sitting over the center of one of, at the time that it was discovered, like, I don't know how many years ago it was, the Haynesville Shale.
Yeah, absolutely.
Was the biggest, at the time, natural gas sort of resource. But we're not using that because the oil prices are low. And so they're not,
right.
They're not drilling much now.
I don't think we're going to run out of fossil fuels in your lifetime, certainly. The only thing we might have is if we keep burning it, we'll see the consequences of putting that much CO2. Now, the planet's not going to stop rotating on its axis, right? It's just there'll be some weather shifting. I mean, look at the western United States. It's in the middle of a long drought. That may be the new normal. The problem would be if we suddenly had that behavior in the American Midwest. Okay, the food belt. Okay, but suddenly they went into a massive drought.
Well, we're in a pretty big drought. Aren't we still in a drought here, guys? I think looking at my lawn, I think we might be. But we did get a dose of rain. We were in like a 7-year-long drought here in Shreveport. It was tough. But hey, Steve, what about this? What about the decline in the sudden decline in species? All these species going extinct recently, and that diversity, right? Does that make our system, our biosphere, sort of more vulnerable?
It's an interesting question. It's a really interesting question because, you know, Scientific American had an article a while back, and it says, how do we deal with this stuff? One way was to go to a completely engineered society.
Huh.
In other words, we just say, screw nature. We're just going to do all of it by hard engineering. Everything will go extinct except us, or many things will go extinct except us, and we will just keep ourselves in, you know, in one piece. And that's a hard, raw approach to it. The question is, why are we going through species extinction? Is it us? You know, are we changing the planet in such a way that other species can't use energy? We're using energy that they can't use, therefore. We're increasingly taking up land space. You know, and they have no place to live. You know, the deer, for example. You see the deer are classic, especially in my part of the world, I don't know about yours, but, you know, we increasingly take over land for agriculture and houses. You know, the deer have less and less and less forest to live in, so they're becoming domestic creatures like squirrels.
Yeah, first of all, hey, let me just say, because we can look out this window over there, guys, you can see my house is basically up that street. And the other day we saw, and we're in the center of the city here, Steve, pretty much. More or less we are, right? A friend of mine saw a coyote, a wild coyote, going towards Centenary's campus across the lawn.
There was a lynx attacking a raccoon on like.
There was a what?
A lynx attacking a raccoon like in the back parking lot.
Did you hear that? A lynx attacking a raccoon.
And when I walked up to it, it just stayed there, and then like
You saw it?
Yeah, and I was frozen, and then like I popped out my taser, and then it ran. But that was the only thing. Because I was like, either I'm gonna run or you gonna run, or we're both gonna die because you're gonna attack me. I'm gonna have to take you.
You
back.
can take that lynx. You don't have anything to worry about.
It was pretty big.
Yeah, well, there, you know, if it was taken on a raccoon, it must
I
have
didn't
been.
even think we got those things.
Wow. But Steve, I didn't actually think that was much of a question, whether or not we were causing the species exterminations. I thought we were. I thought.
Well, that's the most likely source. Every time we track down a particular species extinction, we usually root it back to a human. Because look, think of what has happened. We are by far the most numerous of the large animals on the planet. There's 7 billion of us. Nothing else is coming close to that. Okay, so there's a whole bunch of us, and you know, as there's more and more of us, there's less and less of them.
Yeah, actually, I heard there are a lot of chickens.
Well, yeah. The animals that are doing well are the ones that have hitched their wagon to human beings. Dogs and cats, okay, because we like them. Rodents, because they attach themselves whether we like it or not. The food animals, cows, there's lots of cows in the world. Okay, lots of chickens, lots of pigs. All those animals that we like to eat are out there. You know, fish. Now, fish are interesting because we don't really farm them. Okay, we just go by them naturally, so their numbers go up and down. The fisheries are an interesting problem at this point. You know, we try to control. Remember, I showed you those populations. That's important that we eat those. So we can do better. We can be a little more efficient, but the bottom line is the thermodynamic limit. We just can't get more efficient than a certain amount.
Is there a sort of little equation that one could write, or did Che-san already write it, about that the more energy flow there is, the more complexity there is in that system?
I don't think he did. I think he's looking at the raw numbers. What he is basically saying, and admittedly, this is a paper from a few years ago. What he is saying is if we plot the rate of energy usage by animals, people, this kind of thing, and then we plot it on a graph, like this previous page here, you go back to the previous page, like this, okay, not like that, like this, then what we observe corresponds to what we think of as complexity. We think of the agriculturalists as being more complex than the hunter-gatherers. We think of the industrialists as being more complex. We think of the technologists being even more complex. So that also follows the energy pattern. So he's just making a correlation right now. He's saying if I plot pieces of the world and how much energy they use, gee, it seems to look like the complexity increases with energy usage.
Mm-hmm.
Now, we're kind of assuming things. I mean, obviously, we can probably look. It's pretty easy to see that the industrialists had a society more complex than the agriculturalists. I mean, that's basically the difference between medieval society and modern society. The technologists are using energy faster, but it's trickier to see that, because you have to really look at, for example, our simple this, okay? When I was a kid, we had 10 channels. Now we've got hundreds and hundreds of them. I know that seems ridiculous, but that is something that we have paid for in terms of energy. Okay, that money has to be there. We have to generate that much programming and deliver it to everybody over the internet. Okay, over the cable TV system. And that's an enormous thing that we've done. We've made it, you know, the grid. You talk about getting off the grid. The grid is our new energy distribution system. Okay, we had to develop a grid to get energy to us fast enough. Right? We didn't have, why is, boy, living off the grid, that's a big deal. But that's because you simply can't get energy quickly enough anymore.
Yep.
Okay. I mean, if you want to simplify your life, get rid of all the electrical things.
I can do that if I can keep my iPhone, as long as I can. I can
Yeah, there we go.
Well, Steve, we're coming to the end of our time with you, and we really appreciate it, guys. We're going to have 2 more visiting professors via Skype, 3 more. Or let's see, we got Dante and Scott. No, just 2 more. Godrich is our computer programmer at large, and Hamming will be here in person. And we won't have them for as long as we've had Desjardins, because we needed him for biology too. We didn't have a biologist. But Steve,
you've been. I'm pessimistic. Where you talk to the philosopher and the economist.
Yeah, that's right. Well, the philosopher, he's just going to say we can't know anything, and it's all. He'll cut the legs out from under us pretty good, maybe. But he's a kind sort. So, but Steve, thank you very much. We appreciate it so much. We do. I'll let you know how things go, of course, and I'll be reviewing with them stuff before the midterm, so I'll be going back over this. I might contact you, to sort of get stuff clarified for them, to clarify for them. But
you guys enjoy what's left of your lives down there.
Yeah. Thanks, man.
Oh yeah, he was. I don't know anything. Tell me.